This is lesson 7.3, exponential functions, decay. So just so you know, as we start this section, exponential functions that are in a decay situation are very similar to those in a growth model. We still have the same equation, y equals a times b raised to the x power. We still have x and y representing any coordinate pair that lies on the function. Typically, our x value is time, and our y value is some output like money or number of frogs, right, in a population like we've done. A is still the initial amount that we have of something, like frogs or money. And B is still the growth factor, as we call it, and B still is represented by 1 plus R. The only difference really for decay is that R, our rate, is not growth anymore. Our rate is our rate of decay, and decay means something is becoming less. So if our situation is, again, money in an account and we're spending money, then we are in a decay model because we are getting less and less of it. If a bacteria or a radioactive iodine is decaying, that means we have less and less of it. All right, let's dig into this a little more. Okay, so just to keep this straight, exponential growth means we are increasing something by a certain percentage, and exponential decay means we are decreasing by a certain percentage. So again, looking at our frog population, it said the frog population increased by 10% per year. Or investing money, your money increased by a certain amount of money, percentage of money per year. So now we're going to talk about something decreasing by a certain percent. And let's talk about 75% for a minute, okay? If I mentioned that I have something, let's say I mentioned a minute ago, radioactive iodine, and I have this item and it is decreasing at a rate of 75% per day or per year or something like that. So that's our rate and it's decreasing. So we would often say it's negative 75% because we're decreasing. So think about what that means for our R value. Our rate is negative 75%, which is negative 0.75. If that's our rate, if we're decreasing at 75%, we have to think about what our B value is. So remember, in exponential decay, the rate is negative because the amount is decreasing. So the value of B will be between 0 and 1. Now let me tell you why that is. Let's grab, we know that B, pardon me. B is equal to 1 plus R. Our growth factor, B, is equal to 1 plus the rate. So if we take this rate right here and plug that in right here, we're going to get B equals 1 plus negative 0.75. B equals, 1 plus negative 0.75. If you think about money, this might help. $1 plus negative 0.75, which means you're taking away 75 cents. So $1 minus 75 cents, well, that is 0.25, 0.25. So that would make our B value, our growth factor, 0.25. So see what I was saying right here? Our B value will be between 0 and 1 because it can't be 0 because then there is no growth or decay. And it has to be between 0 and 1 because we're taking that 1 and we're adding our negative rate. So again, 0.25. So this is an example of a negative 75% exponential decay situation. Remember that 2 here is our original amount. 0.25 is our B value here. A B value of 0.25 means that the rate was negative 0.75. And we're still, again, raising that to the x power. Okay, I'm going to talk about a real world situation that some of you might be familiar with on the next screen. And then on the fourth slide, I am going to go over a graphing example, just like with our growth example in the previous lesson. Okay, so what we have here is an example of exponential decay that you may or may not have realized. And that is March Madness. Okay, or in fact, any tournament bracket. So if you've ever competed in anything and have been in a tournament, that is an example of exponential decay. All right, let's think about this for a minute. In March Madness, and again, if you don't watch basketball or whichever sport it is, it's okay. What we do with the tournament bracket is that on all of these little lines over here, way over to the right and way over to the left, the team names are put in there. So maybe the Golden Gophers are right here and against the Badgers of Wisconsin. So go Gophers. But anyways, so we have a team listed on every one of these lines. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'm just going to stop there for a second. 16 of them right here. And then we'd have another 16. So that's 32. And then another 32 over here. So we'd have 32 over here, 32 over here. That's 64 teams. There we are. Our initial amount of teams in this tournament is 64. Now, after every single game, assuming that no ties are allowed, which they're not, we have to have overtime, whichever team wins goes on to the next round. Okay? Whichever team wins here goes on to the next round. And the team that loses is done. So then after all of those games are played, we now have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 teams left over here and 16 teams left over here. We now have 32 teams left. Well, that makes sense because out of the 64 teams, half of them win and half of them lose. So we have decayed by 50%. Now let's think about that 1 plus r and that b. So our b value is equal to 1 plus our rate. So our b value is equal to 1 plus what percentage of teams are kicked out of the tournament after round 1? Well, like we just said, half of them. So, 50%. So negative 0.50. Well, 1 plus negative 0.50 is, of course, 0.50, right? Half and half. So our b value is 0.5 or 0.5, which is what goes here. So we can find out using this equation. Again, 64 is our original amount of teams. 50% of them get kicked out every round. We can find out how many teams are left after however many rounds. So let's say after 3 rounds. So if I put, let's just make ourselves a little t-chart here. If I put a 3 right here for x, I want to find out how many teams are left after 3 rounds. Well, we need to take 0.5 and raise it to the third, which is 0.125. And then we need to multiply that answer by 64. And that answer is 8. Now, if you want to go ahead and check that on your calculator, that's not a bad idea. Again, put 0.5 into your calculator, raise it to the third power, and multiply it by 64. Or you could have just typed it straight across. So type in 64, parentheses 0.5 there, raised to the third power. What you're going to find out is 8. Well, again, that makes sense because after first round, second round, after the third round, how many teams are left? 1, 2, 3, 4, 5, 6, 7, 8. And they call that the Elite 8. All right, so this is how exponential decay works. Okay, so let's take a look at an example of graphing exponential decay. Sorry, I'm just kind of making those fit a little better. And let's use the values just like we did with growth. Let's use 0, 1, 2, and 3 for our variable x. So we are going to plug those, again, plug the value in of x, which is typically time, in for that exponent, and then simplify and find our y value. So we have this. We know anything raised to the 0 power is 1. So all of this is 1, and 12 times 1 is 12. And then we're going to plug in a 1 for x. Notice this time I have a 1/4 in for my b value instead of a decimal. I want to point that out as I'm working here. Sorry. 1/4, you guys remember, is the same as 0.25, right? So if we wanted to rewrite this equation as y equals 12 times 0.25 to the x power, we can. That's exactly the same equation. And when we do our math here, we have, well, 1/4 raised to the first power is just 1/4. And 12 times 1/4 is 3. Again, if you need your calculator on this, that is absolutely fine. Just multiply 12 times 1/4 or 0.25 raised to the first power. And we're going to take y equals 12 times 1/4 raised to the second power. Now be careful with this. Again, if you're using your calculator and you're using 0.25, that won't be a problem. But if you're doing it by hand and by brain, 1/4 raised to the second power, think about that for a minute. That is 1/4 times 1/4, which is 1/16. And then 1/16 times 12, or 12 times 1/16, is a decimal, and it is 0.75. All right, so 0.75 or 3/4. And then we're going to put in a 3 here. 12 times 1/4 raised to the third power. Again, if I did my math here, 1/4 times 1/4 times 1/4 is 1/64. And 12 times 1/64 ends up giving us 0.19 when rounded a little bit. Okay, so let's put in our points on our graph and see what exponential decay looks like. So 0, 12. 0 along the x-axis and up 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think I counted that right. So there's that point, 0, 12. And now we have 1, 3 right there. Oops, a little bit off there. I'm going to try it again. I put 3 dots. We get there. All right, there it is. And then we have 2, 0.75. So that's going to be right around there. And then 3, 0.19. We're getting really close to our x-axis right there. So that is what our curve looks like. And I'm going to draw that in as best I can. And I want to point out, oh, that's pretty bad. I want to point out that it should not cross the x-axis. I want to talk about that quick. This is an important point. This curve is coming through and it's never, ever, 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 ever going to hit the x-axis. Let's think about why. Let's say this is money, $12, and I will have 1/4 of it after each round. 1/4 of 12 is 3, 1/4 of 3 is 0.75, 1/4 of 0.75 is 0.19. If you keep taking 1/4 of a number, a fourth of it, a fourth of it, a fourth of it, you will never get to a negative value. You're just going to get to a very, very, very small amount that approaches 0. So it will never cross. So be careful when you graph your curve. So that's exponential decay right there.